Thank you, Professor Chandrasekhar. It's indeed a great pleasure for me to be here this morning and to speak to you. I thank the Academy for giving me this opportunity this morning. I know that this is a very mixed audience, and therefore I like to keep my talk as broadly interesting as possible so that most of you leave this talk with a message which I hope to convey. So I think I'll try and be. I'm going to cover a very, very wide spectrum of topics within this broad area, but I don't want to get into depth of each because then I will lose some of you, but I like to give you a flavor of why we do these things and what's the purpose of doing this kind of a chemistry. This word sustainable today is a very interesting and oft repeated word, and I think if you just do a Google today, you will get something close to, today you get something close to 100 million hits on the word sustainable, okay? It's one of the largest hits that you can get. If you did Twitter today, you get something close to about 40 million hits on a Twitter on a word sustainable. It's a point of conversation today in this world across many, many people, and I don't want to belabor on this topic today, but I think it is driving to a large extent science, in my opinion, also, because the sustainability is a bedrock which is also driving science today in a very large extent. And therefore, everyone who practices science and technology is in a way asking, am I contributing to this broad goal of sustainability? And especially when you deal with organic chemicals and organic materials, I think the sustainability word assumes a hugely important question, because as organic chemists and organic people who deal with organic materials, we always wonder whether the chemistry that we are practicing, the materials that we are using, are truly sustainable by today's standards that we wish to judge by. So this word sustainable, I think, is a hugely important word today, and I think every one of us who practice science and technology in some way or other are intersecting this term sustainability in our daily activities. Now, why is it that I'm saying organic chemicals and materials? Because I'm going to be talking about organic materials a little later. We all depend exclusively on fossil fuels for organic chemicals and materials, and I don't want to again get into the details of what that implies. And like it or not, we generate a huge amount of waste when we use organic chemicals and materials, and that's also a huge problem for global sustainability. And therefore, as at least organic chemists and organic people who deal with organic chemical substances, I think sustainability has a deeper meaning in our daily lives. Well, it is a point of conversation today. There is no doubt about it. It is a key concern of science, technology, industry, and society. And I think that's one of the reasons why it is in this one term that we intersect a very large number of stakeholders. And therefore, as people who are responsible to the society, we can't ignore this term. In fact, right this year, in January of this year, the American Chemical Society finally woke up to start a new journal. And this new journal is called the Sustainable Chemistry and Engineering. There have been many journals, I guess, but I think appearances of journals to some extent also indicates the kind of interest that the science is generating. And this journal has just begun in January 2013. Well, the question that all of us keep asking periodically is, can the chemicals and materials needs of humankind be based on the concept of sustainability of both resources and environment? And I think that's the broadest question that you can ask, and hopefully that will drive a whole lot of research agendas for many, many people. Well, I just want to leave you with only one point, and I think all of us see this bottle here, okay? Look at this. This is a bottle that all of us consume. It is made of a quintessential, what I call a miracle of chemistry, which is called the polyethylene terephthalate. All right? So it's called the miracle of chemistry. In fact, DuPont started the logo, the miracle of chemistry, with polyethylene terephthalate and nylons. Okay? Well, 30 billion liters of bottled water is what we consume annually, and as we speak, every second that we live in this planet Earth, we are throwing away 1,500 bottles. Every second that we live on this planet Earth, we are all throwing away 1,500 PET bottles of different shapes and sizes. Many of them enter into waste dumps, many of them enter into waterways, and you know what the consequences of these are. And I think all of us are responsible for this, right? Why are we doing this? Okay? Each one of us. In fact, I just wanted you to know, many of you may not know, there is a symbol by which we recognize plastics. And I don't know many of you know that. If you look at this bottle, at the bottom, you will see the sign E1. Okay? You will not see the word PETE. You will see the sign 1. That means this bottle is made of polyethylene terephthalate. So that a common man also knows that this is a bottle that is made of polyethylene terephthalate. He doesn't have to be a chemist. He will still know that. And that's the consequence of what is called a non-sustainable use of a material. I am not saying polyethylene terephthalate itself is non-sustainable, but this is a non-sustainable use of a material that we all merrily consume and throw away. Okay? The question is, I will not talk about this. There is a separate talk I have on this question, which is what is the solution? Okay, but I'm not going to be talking about it today. That I give it for some other audience. What is the solution to this problem? Okay, because this problem is not going to go away. This problem is in the increase. The use of polyethylene terephthalate in bottles is at the rate, growing at the rate of 16% as a compounded annual growth of rate. Okay, and with more and more people coming onto this planet Earth, and more people able to wanting to afford what is called quality water, we think that this water is of high quality. I see that's my problem. We all think it is of high quality, but we assume that this is a high quality water. We all buy and consume, and we throw away the bottle. Okay? Well, there are solutions to this, but I will not talk about it. Well, therefore, the question that we keep asking again is there a virtuous cycle in materials in terms of what is it that we can do? And that is, in fact, this is where biology essentially intersects chemistry. Can we make a biomass? Can we convert biomass into chemicals and materials? And when we throw it away, will this go back into carbon dioxide and water? You know, and that's the virtuous cycle that I think everybody's dream of. I think it is a dream at this point of time. It doesn't exist, but it is a dream worth pursuing, because I think the future of mankind depends upon the realization of this dream. Well, now let me come to the chemistry. That's a little bit of introduction. What have we been doing in the lab for the last few years, at least for the last 7 to 10 years, is looking at, is there a sustainable platform for making what we call a class of polyesters. This is also a polyester, but this is not a biodegradable polyester, because this has an aromatic group. Okay? So the question is there a class of polyesters, we call it aliphatic polyesters, that could be a more sustainable material for certain applications, and we will be extremely fortunate if we can find an aliphatic polyester by which you can make these bottles, which when you throw it away will decompose into carbon dioxide and water. Okay? Now that's the miracle material that everybody is looking for, but that's the question that we can all ask. Can we find a bottle that will decompose into carbon dioxide and water when you throw it in the dumps? All right, so that's the chemistry that we are looking at. So our preoccupation has been looking at the chemistry. A quick chemistry 101 introduction for those of you who may not know enough of polymers. Polymers, especially polyesters, are classified into 3 types. One is called the aliphatic polyesters, which is what I'm going to be talking about. The other is called the aliphatic aromatic polyesters. That's what these bottles are made of, the aliphatic aromatic polyesters. And then there is what is called a fully aromatic polyesters. I won't talk about this. This is a special topic. This is not important today. Well, these are the ones that are persisting in the environment. This is what, of course, you make the bottles out of them. It's a curse, but this is also clothes practically 80% of the humanity. So all the dress that you wear comes with a polyethylene terephthalate, okay, PET, which is a polyester. So obviously there's both a devil as well as an angel in this material, right? So the bottle is a devil, whereas the clothes that you wear is something that is clothing humanity. There is not enough cotton in this world to clothe 7.5 billion people in this world. Well, this is polyethylene terephthalate. There are other materials, other classes of materials. This is another class of material. All of you use a credit card, right? Or a smart card. Every credit card that you use is made of this material, okay? All right, so that's something that you may not know. When you use a credit card, every credit card that you use is actually made of an aromatic acid and a cyclohexyl, diol, okay? All right, so that's the story about aromatic polyester. I'm not going to be talking about it either. But the problem is that this class of materials, we consume 60 million tons per annum, okay? All of us, the whole humanity, of which 1/3, which is 25 million tons of this material goes into making bottles for various applications, of course. Drinking water is one of the major ones, but there are other bottle applications. In the kitchen of every woman, you will see a whole lot of PET bottles, where you store your kitchen things, okay? So that's what 25 million tons of this material goes into making bottles, all right? Now we have an alternative. The alternative is a fully aliphatic polyesters. And I can tell you, there are many aliphatic polyesters, and I'm going to be talking about it in a few minutes, which have properties exceedingly close to aromatic polyesters. And therefore, potentially there's a substitution possible. All right? What is limiting? Why is it that we are consuming less than 200,000 tons per annum of this material? Okay? If there is a solution here, then why are we not using them? Okay? Because the chemistry is limiting, and I can also tell you, for those of you who are biologists, the biology is limiting. Okay? Because much of the monomers here comes from fermentation chemistry, and that's a limiting process. And therefore, if somebody can enhance, fermentation science and technology, you have, of course, a much greater opportunity in many of those raw materials. And therefore, I'll come back to that in a minute. But in spite of the fact that these kinds of molecules have been in existence, and people have been looking at it, some of them are even used to some extent commercially, and I'll talk about one that is becoming increasingly important commercially. These are consumed today at less than 200,000 tons per annum. Look at the 60 million tons of that, and less than 200,000 tons per annum. So there is something which is limiting here. And that's the question we are going to ask. What is limiting here? How can we, let's say, what is the approach to at least eliminating some of those limitations? Well, the most important of this, and that's something that we have spent considerable amount of time in recent years, is the polylactic acids, okay? And I don't have to tell you to this audience what's the importance of lactic acid. In fact, I told you, that's what I said here, that this is where biology is limiting, okay? I mean, if I can make lactic acid by fermentation industrially at a cost that is justifiable, this can become a huge replacement for this, okay? And for those of you, I'm not going to be talking about that part of it, but biology is limiting in making available enough of lactic acid at an affordable price to meet this application, okay? And we all know what's the problem with lactic acid bacteria, okay? We all know that. All right, but today, a small amount of this polylactic acid is being made, okay? When I say small amount, it's about 100,000 tons per annum. It's a very tiny amount on a context of 60 million tons of polyester that is being consumed. Bottles you can get, as you see here, they're from biodegradable bottle. You can buy a bottle today, but it's too expensive. In fact, it's more expensive, much more expensive, that the water becomes very expensive in the process, okay? So that's something is an issue. But if you are a green, person, you won't mind buying that bottle, okay? Without understanding, of course, that you don't make any impact, but that's the way you do that. Well, if you want to get that bottle, you will see no longer the sign 1, you will see a sign 7, okay? So if you go anywhere outside this country, you will find bottles, and you can go and look at the bottom of the bottle, and you will see a sign 7, which indicates it is made from lactic acid. Okay? And of course, there are many other products that are being made out of this today. They are attempting to make of these products. Well, what is the big deal? The big deal is that you leave this product in a typical composting environment, and over a period of 1 month, it simply vanishes. Okay? So that's the advantage. So you just keep it in a composting pit for a month, and the bottle will completely vanish without a trace. And that's the advantage of this bottle. So there is a solution. The question is, unfortunately, the solution is not today enough, in terms of cost and material properties. And I'll tell you in a minute what the material properties are. So you can make it compostable. You can make it very similar to PET in performance. Of course, it has some deficiencies, and we'll talk about it, but it has the opportunity. You have an opportunity to do this. And of course, the chemistry is very simple. In fact, the interesting thing about this chemistry, before I do that, you can see what's happening today. This is just a SciFinder search on polylactic acid. You can see here that there is something like 2,000 and odd patents every year and 2,000 and odd publications every year, just on polylactic acid. And that's increasing with time. And you can see, therefore, why sustainability is driving a research agenda. Okay, and that's very clear. Okay, you see a clear indication of why sustainability is driving a research agenda. And if I just do a SciFinder search on aliphatic polyesters in general, I leave out the polylactic acid in this. It's not that attractive, but still it is something which is significant. And in fact, there is a much greater opportunity here that people are still not exploring at this point of time, and I will talk about it in a minute. Well, this chemistry, and that's what I titled my talk, is a very old chemistry. Okay? This chemistry takes us back to the history of polymer science, way back to the late 1920s, early 1930, when there was a gentleman which we all know, which is called the Wallace Hume Carruthers, who created this chemistry. And therefore, this chemistry is not new chemistry. Okay? And therefore, the question is, this is what amazes us, that in spite of the fact that 80 years we have lived with chemistry, we haven't found a way to make use of this chemistry in today's world. And therefore, there must be something which is really limiting in this chemistry, and that's what we are going to be looking at. What are the issues? Okay? The issues are very simple. In fact, between 1929 to 1935, Wallace Carruthers published something close to 28 papers only on aliphatic polyesters. Okay? And that was the simplest chemistry that he could think of when he wanted to make what is called the large molecules. And in fact, much of the work of Wallace Carruthers is available. It is free on the web for those of you who want to read it. It is published in 1940. He died in 1937, as you know, of tragic circumstances. Wallace Carruthers always used to carry an ampule of cyanide in his watch. Okay, I hope you know that. And he consumed it in one moment of depression. He wrote in his lifetime 54 papers, which is 10 years, of 400 pages, considered as classics in polymer science. In fact, there's a book written on him, I think which is appropriate, which is called, he died, you can see, at the age of 40, and he says he probably did more chemistry than anybody did in a lifetime. Okay, and that is Wallace Carruthers. So I think we need to pay a tribute to this gentleman today. And what did he say? He asked a very simple question. He said, if two bifunctional molecules, which is one is a diacid, the other is a diol, and of course it could be also a diamide, if they react, he says you can produce a chain polymer of a lower or higher molecular weight, or he says you can produce a smaller or larger ring which does not contain the reactive group. That means, he said, you can have either an intramolecular esterification reaction, or you can have an intermolecular esterification reaction. And he said, under what conditions that one is favored over the other? And that's a fundamental question he asked. Okay? And that led us, and in fact, in a classic review that he wrote, and I want, if there are students of polymer science in this audience, I would encourage them to read this review published in 1931 for the precision with which he expressed his thoughts. And in fact, he did this analysis. He said, what will happen if I take a whole lot of hydroxycarboxylic acids. Okay? And I try and polymerize them. Okay? And in fact, much of the results he didn't have at the time, but much of it was speculative, but much of it was also based on very sound principles of bonding and conformation. And what he said was, if I have glycolic acid, if I have lactic acid, and then if I have beta hydroxypropionic, gamma hydroxy, butyric, delta hydroxy, epsilon hydroxy caproic, well, he said that you all can get cyclic molecules. And we all know this in organic chemistry, that it's very easy to make these cyclic molecules. And he also said that some of these cyclic molecules can, of course, undergo, under a different set of conditions, polymerizations to form larger chain of polymers. Okay? And he kept on talking about this, and of course he said that if it's beta hydroxy, you will not get anything, you will get acrylic acid. If it is gamma hydroxy, you will get a very stable delta lactone. If it is delta, you will get this valero. If it is this, you get a epsilon caprolactone, and variety of such cyclic monomers. In fact, these monomers are all today very well known, and we all know how they polymerize, how they don't polymerize very well. But he made this table in his chemical review article in 1931. I think it was a very clear exposition of a chemistry that very few people understood at that point of time. He also, in fact, this is a review, this is the cover of the review, and he actually wrote a chapter in the review which is called the self-esterification of hydroxy acid. Lactic acid is the alpha hydroxycarboxylic acid. And therefore, he said, in fact, the earlier table, I pulled it out from this chapter, and therefore he asked this question: if this is a reaction that we are talking about, let's say a lactic acid, which undergoes esterification reaction, and you can get polylactic acid. Or a lactic acid can undergo some kind of a cyclization process and get into a lactide formation. He asked, on what factors do the relative rates K1 and K2 depend upon? Okay? What is the importance of gender? In fact, he did not give those answers, by the way, but he raised those questions, and he didn't have, at that point of time, enough of analytical tools to provide all these answers unequivocally. What is the importance of the general acid catalysis in these reactions? In fact, this is something which is hidden in his discussion. It is not obvious, but it is hidden in the discussion. Can larger oligomers undergo thermolysis to large rings? This is a question that he raised. In fact, this was a time, as you know, that the large cyclic ketones of Ruzicka were being synthesized at that point of time, and therefore he said that is it necessary that large rings will form or will not form? And of course he tried to argue this point based on understanding of chemistry at that point of time. And if this is the last question that I have asked here, in addition to those, if ring formation limits the chain growth reaction, is there an alternative method to make high molecular weight linear aliphatic polyesters? Because if ring formation is something which is an inherent problem in all such polymerization reaction, is there a way to avoid this reaction? And that's a question that we will also try and answer very quickly. Okay? So one of the things that we started doing some years ago was go back to this chemistry which Carather studied, okay? And to some extent left a few questions unanswered in Carather's early work, and we said, can we try and kind of reopen some of these issues using the tools that we have today that Carather's unfortunately did not have. Many people gave up on aliphatic polyesters very soon because aromatic polyesters were invented very much little later by both at the ICI in Wilmington and at DuPont, and therefore a whole lot of interest was diverted to aromatic polyesters, and aliphatic polyesters was left as a small baby somewhere on the way. And I think we picked it up some years ago, and there's been increasingly interest, as you can see in the recent years, in the area of lactic acid polymers. What we did was we also looked at catalyzed polycondensation, because we also realized that the general acid catalysis may not be the right approach to make reasonable chain lengths of oligomers. We picked up what is called a water-tolerant Lewis acid catalyst. We also realized that water removal is going to be limiting in these reactions. As the melt viscosity increases, you're going to have problems removing water, so we tried to address that issue to some extent. I won't get into the whole detail. We also realized that this is a reversible reaction because the water can also hydrolyze the polylactic acid, and therefore the water, I mean, that's one of the reasons why it's the rate limiting reaction. And we also wanted to probe very deeply into what happens to macrocycle formation, and that was something that we were very keenly interested. To cut a large story short, and I think I want to leave that, using a combination of techniques, and this has been published, we established that cycle formation is something that is impossible to achieve as long as you go beyond a certain temperatures. And as we all know, if you want to grow long chains of polymers and you want to disengage small molecules while doing this reaction, you need higher temperatures. And what we found was that below 150 degrees centigrade, you can get low molecular weight oligomers of polylactic acid, not great use in application. But as you increase the temperature to drive the equilibrium to disengage the water from the melt, you start, or for the, in this case we also use a solvent, you start making cycles, and you can see that now I can start making cycles which is pretty large. In fact, I can make cycles here, very large cycles. In fact, at 190 degrees we found out that there was no linear polymer. These are all cycles. There is no end groups at all. And that's the reason why the reaction will never go, because there are no reactive end groups. So the whole reaction is driven by an equilibrium in which the cycle formation is the one that makes the reaction goes ahead. Okay, so as we keep increasing the temperature, the reaction starts cyclization, and then you get these huge macrocycle rings that are formed, and that's the reason why these reactions can never go to very high molecular weights. And that's the answer that we got out of this technique. We also looked at this reaction for another, looked at this phenomena for another reaction, which is a very simple reaction, which also was studied by Carruthers, which is a reaction of dimethyl adipate with 1,4-butanediol, okay, which is a very simple reaction of an ester with an alcohol to form a polyester. And we figured out that what happens again, we looked at this by a variety of methods. We looked at a lot of side reactions. Of course, there is a cyclization at the chain end to extrude a tetrahydrofuran molecule, which again you loses the chain end. You have ring closures, you have backbiting reactions, and we could pick up all of these by a variety of methods. And you can see here that the net result of it is you keep losing the end group as you drive this reaction. In fact, cyclics of dP is equal to 2. That means 2 units of monomer were detected even at 125 degrees, whereas cyclics of dP of 2 to 12, 12 means 12 monomer units, the macrocycles were detected at 180 to 220 degrees centigrade. And this is the basic problem in trying to build molecular weights out of linear polymers, out of aliphatic polyesters. If this problem was not there, then I could have made all the bottles with this material, okay? There would have been no problem. But then, unfortunately, that's an issue. So how do we make this polylactic acid? Therefore, I said people are making it. How do we make it? Well, it so happened that you can take a cyclic lactide, okay? You can take a cyclic lactide and actually make the polylactic acid. You can make a glycolide and make a polyglycolic acid. You can take a lactide and you can make a polylactic acid. But this requires a different mechanism. This is no longer a simple polyesterification reaction. This is we call a ring opening polymerization method. This is actually driven by entropy. It is no longer driven by equilibrium kinetics. It is driven entirely by entropy, because you're opening a ring and to make a linear polymer, and it's a catalytic reaction. Now this is done, this can be done, but this is a more complicated process, and there are limitations to this process. What are the limitations? First of all, if you want to make a lactide, you still have to start with lactic acid, and lactic acid is not a neat material. Although we call it lactic acid, commercial solutions, as you get it out of the fermenter, 90% lactic acid actually contains only 60% of lactic acid. It contains a substantial amount of a dimer and a large amount and a small amount of a lactide. And therefore, you have to actually, this is something which is inherently present, and this is essentially due to what is called a general acid catalyzed oligomerization and cyclization that occurs as you keep storing lactic acid. In fact, storage of lactic acid solution is indeed a huge problem. Well, you have to isolate this and crystallize, and that's not an easy task, although people do that, but it's not an easy task, and one of the reasons why the costs keep pushing up. Well, you can do something with this, but this is not an easy monomer. It sublimes at 95 degrees centigrade. So it's very difficult to handle this monomer, especially in polymerization chemistry. The second is, as I told you, this mechanism of polymerization of this is entirely different. Therefore, it's very difficult to co-polymerize this with anything, because you need to find compatible monomers which will co-polymerize by the same mechanism. And that's not easy to find. There are not many such monomers. Well, one can avoid all this problem by esterifying this to a methyl lactate. You can distill methyl lactate, pure methyl lactate. It's easy to do that. But unfortunately, methyl lactate is a volatile liquid. In fact, at 130 or 120 degrees, it completely gets out of the system. So how do you keep it within the system? I told you all reactions of polyesterification require something like 150 to 200 degrees centigrade. And that's the challenge, because it's impossible to keep this monomer inside a pot beyond 120 degrees centigrade. So all these are the complications. So one of the things that we have been looking at is, can I look at an AB monomer which has a boiling point about 250, high vapor pressure, easily purified, hydrophobic, preferably a methyl ester. So that's a kind of a definition that we started putting. And he said, if I can find such a monomer, maybe I can do this chemistry far better. And that's the question that we address. This is currently in progress in the lab research. We have actually made one monomer, and that is a simple dimer of a methyl lactate, which is an L-methyl lactate with an L plus lactic acid. Okay, and this is a chemistry that one can do. The interesting point is, in fact, we estimated this earlier by purely from theory, and it looked like that this looked like, and this is indeed a very high boiling monomer. This boils around 260 degrees at atmospheric pressure. Okay, 107 degrees at 5 millimeter pressure. It's a great monomer to deal with in a pot, for polymerization. Okay. It can be purified by distillation, which is very nice, which is easy to purify. And then the interesting point is, now it is no longer an acid. I don't have to worry about a competing general acid catalyzed oligomerization, which normally competes in lactic acid polymerization. It is an acid, and therefore we think, and we have done this reaction now, we think that I can now transesterify the hydroxyl with a methoxy group in a neutral condition, which is a titanium isopropoxide, which is a very well-known catalyst, in a two-stage polymerization between 150 to 190, and of course there is a vacuum to remove the methanol, and we can actually now produce polylactic acid of much higher molecular weight with far limiting amount of cyclics. And I will not get into the detail at this point of time. The interesting point is that I can distill this monomer out of a pot without forming the cyclic lactide. Okay, I can distill this without a pot, which indicates to be, which is the question that Carruthers asked, was this a general acid catalyzed reaction? And actually the lactic acid dimerization to lactide is a general acid catalyzed reaction, and therefore if I eliminate the general acid catalysis, I can actually take a dimer of lactic acid in a way, or a methyl lactate and lactic acid, and distill it and get the product without cyclization, which I think is a very significant observation that we have made in the lab now. And of course this is going on at this point of time to look at other opportunities. The interesting point about this monomer is that this is a linear monomer. I can now co-polymerize. I don't have to worry about a cyclic ring opening polymerization mechanism. I can apply that classical polycondensation or a step growth polymerization mechanism. Now, well, the other question which begs us at this point of time is that if lactic acid polymers cannot be made by chain extension, by a polycondensation chemistry, is there some other method to do this? Okay? And we have explored many methods in the lab. Unfortunately, nothing has been so successful, but some of them have been interesting, but nothing have been very successful that I can now say that I can make a bottle out of them. But hopefully we will get there someday, but that's not true today. We can take coupling. We can do coupling of preformed oligomers, and there is a method of doing this. We also looked at, one of the problems I talked about in many of these reactions is the removal of water, okay, or removal of small molecules, because then I have to increase the temperatures. At high temperatures, I get great propensity for cyclizations, okay. So can I convert a reversible, which is normally an equilibrium, reversible chain growth reaction to an irreversible reaction? And lastly, we have also looked at conformationally constrained monomers where I can prevent cyclization completely because I introduce conformationally constrained monomers. I will just quickly run through this because I think I'm running behind. How many minutes I have? About? Huh? Okay, couple of more minutes. I may be behind a few minutes. I'll come back. Okay, one is I can couple. For example, this we have demonstrated. We can take a polylactic acid oligomers, which I can make without much of a cyclic. I told you below 150 degrees centigrade, which has a rough dP of 15, and I can couple them to make a chain dP of 500. And this is simple coupling reactions. And this is something that organic chemists practice very well. And I think we have just applied this chemistry to polymer science, polymer chemistry. And we can do this coupling reaction. And this is one approach that we have looked at this point of time. There are some problems with this approach, and that I will not belabor. The problem is that there seems to be a chain termination through an O-acyl to N-acyl urea, and that's a problem, okay? So in many of these, in the polymerization, as long as I have the O-acyl urea, I can get the chain growth. Once I get the N-acyl urea, the chain terminates, and we find evidence that N-acyl urea formation limiting the chain growth reaction. But we can think of eliminating that, and that's something that we are trying to do. The other one that we can do is a very interesting chemistry that we have recently done, and that is you make a oligomer of a dihydroxy derivative, okay, which is a chain terminated dihydroxy oligomer of a aliphatic polyester, okay. And of course there are methods by which you can make it, you can characterize it, you can show that there are 1.9 hydroxyl groups per molecule, and then you can do the MALDI and show that you have the right N groups here, so that there are no cyclization, there are the right N groups. And now what you do is, we did this chemistry, and this is a very interesting chemistry. You take a molecule like divinyl adipate, okay, and you do this reaction, which is a kind of a transesterification reaction. And as many of you will recognize, that the byproduct of this reaction is actually vinyl alcohol, which is acetaldehyde, which gets out of the system. It's irreversible. So I have converted a reversible polycondensation reaction to an irreversible polycondensation reaction. In that process, I can now make at least jump the molecular weights from 2,700, which is what I can make by classical methods, and take it to something like 37,500. Well, this is a chemistry which looks promising at this point of time, and of course we are looking at a variety of vinyl esters as comonomers in this kind of a reaction at this point of time. And I think this looks like a very interesting way, because here I don't have to disengage a molecule as I do a polymerization, which is the conventional Carothers chemistry you had to do. Well, the other one is, if I introduce molecules of this type, which is little bit rigid in structures, I can minimize cyclization, and I think it's obvious why, okay? And because I introduce conformational restriction in the chain, and therefore the chain ends don't find each other so easily, all right? So one of the things is we have done extensive amount of work in this area where we looked at a variety of monomers, and many of these monomers can be very easily made, but they are not commercial. And then we tried to make polyesters from these at this point of time, and then you can see a whole lot of polyesters that we can make, okay? And they're all aliphatic polyesters. They have the same properties like polylactic acid. They were all under compostable condition, they were all biodegrade, okay? But the problem is that, of course, there's no issue here. You can make these, and as long as you introduce some of these kinds of rings into the chain, you can eliminate, the possibility of ring closure. I'm finished. Ring closure, and therefore you can eliminate possibilities of cyclic formation. So that's about the three strategies I talk about, which can possibly eliminate the chemistry that can eliminate the weakness in aliphatic polyester chemistry that we have been looking at. I'm going to stop here at this point of time. Since I didn't have the time to look at a few other things, and I just get to the last slide. And I think the message, therefore, I have tried to convey here today is that you take an old chemistry, which is a polycondensation chemistry of a diol with a diester or a diacid, which is as old as 80 years old, and you understand what is limiting in this chemistry, and you try to see what you can do to overcome some of this limitation. And hopefully, if you do that, you probably can still look at new chemistry out of something which is as old as 80 years. And that's what my colleagues have been doing and helping me to do this. Sandhya was the one who first started this activity in my lab, and she made all these bicyclic monomers and the polymers thereof. Shamrai did a detailed study on lactic acid polymerization and understood what's limiting chemistry, which is limiting in lactic acid polymerization. Neeta Kulkarni looked at the aliphatic polyesters. Yogesh is somebody who is just now working with me in making these high boiling AB monomers, which I hope will hopefully overcome some of the limitation. Amrita, I didn't talk about her work. We are doing a lot of work on what is called branched polyesters for certain application, and she is working in that area. And these are some of the students who are working in some of those allied fields. Deepti is actually an Academy Science Summer Fellow who is also working in this area with me at this point of time. So I'd like to thank all of you for your very kind attention. Thank you.
Yeah, we may have a couple of quick questions we have in. Yeah. Puran Prasad.
If compared to using this bottle, okay, if you use a bottle that is made of a biodegradable material, okay, you can actually reduce carbon dioxide by 60%, okay, compared to making use of this bottle, okay. So that there are calculations of life cycle analysis that shows you right from the feedstock to the end user, those kinds of bottles. Yeah, those bottles are not available, unfortunately. That's a problem. Yeah.
All right. Yes.
Have you attempted making polymers of lactic acid using biological means or using some enzymatic methods?
You know, the problem with biological means, I mean, in fact, this is an area which we can debate separately, is, you know, can I make a few 100,000 tons of these materials in meaningful manner, okay? As you know, lactic acid aqueous solution itself, you know, is available as out of the fermenter only as a 10% solution. And it takes me a lot of energy to get it to 90%, honestly speaking, you know. Now the question is, I mean, you tell me how will you do that? In principle, yes, it's possible. People have tried. The question is, what's the dilution? What's the effect of concentration that you can get, you know, in terms of process? That's right. And the question is, we are talking today about it can be done, but I'm looking at the economics of doing so because you can see the numbers. You know, we are talking about 25 million tons of bottles, you know, that we are consuming today, and which is, 25 million tons of polyester that we are consuming today. The question is there a viable biological process? Actually, the more important thing is, you know, can I make the lactobacillus function at pH 7? If that somebody can find me a lactobacillus that can work at pH 7, it's a huge, you know, opportunity for this. Today I had to work at pH. I mean, I had to neutralize a whole lot of you know, the fermenter broth because the thing. And the second thing is, again, a biologist should tell me, a fermentation science people should tell me, how can I make it less fastidious? The amount of nutrient I need for lactobacillus is so expensive, you know, that it kills the economics of making lactic acid. Yeah. People have tried that. Unfortunately, the yields are very low, but compared to the carbon efficiency that you get in lactobacillus, you know, that's it. Okay. So.
Okay, one last question. Dr. Vandana.
You have always tried reactions at high temperature. Have you tried low temperature? Because it is a great pity we are having cellulose with the reactive position and we are not using some. You can add
You can do it at
amino group.
Yeah, for example, one of the reasons we did this adipate, vinyl adipate type reaction is I can do those reactions at 110 degrees centigrade against 200 because I don't have to remove you know, a small molecule from a growing viscous polymer melt, okay, or a polymer solution. And therefore, if I use an irreversible polycondensation chemistry, we are running those chemistry today about 100 to 120 degrees centigrade. which is also the right temperature I need in order to avoid the cyclic formation. So I think, if you tell me can I do it at room temperature, well, I can do it at room temperature. There are what is called enzymatic transesterification reactions that people have tried at room temperature of an acid with a diol. But unfortunately, these reactions are not very, very efficient. You know, they are very, very nice and interesting, but they are not very efficient.